these are light-dependent reactions. I drew a structure of a thylakoid membrane and its lumen. And we see various different structures such as photosystem 2 and photosystem 1, or PS1 and PS2. PS1 and PS2 both contain pigments such as chlorophyll, which help absorb light coming from like the sun. So the chain called the electron transport chain starts with sunlight coming into the photosystem 1, sunlight, and it meets low energy. We have some low energy electrons like right here. We have low energy electrons, but it's in a low energy. And when the sun meets these low energy electrons, it charges the electrons. And the low energy electrons are found at the bottom of the photosystem too. And it charges these electrons and causes them to become high energy electrons. And this is because of the sun and the chlorophyll inside photosystem 2. The pigments, they absorb the light and increase this electron's energy and makes it a high energy electron. And this electron is then passed into a system of like a system of a chain. So first we're going to see that this high energy electron is going to go into it's a complex. It's just A, and then we're going to see it go to B, and then it goes to C, and then it goes to photosystem 1. But let's explain this real quick. So why do we see that the high energy electrons go from A to B, then to C? This is because each complex, like so A, B, C, each one is more electronegative than the past. So B is more electronegative than A is more electronegative than PS2, C is more electronegative than B. So when the high energy electrons from PS1, they want to go where it's more electronegative. So they're going to go to A, and then they're going to go B, then C. And so every time that the high energy electrons is passed on to a new complex, it actually releases energy, right? And we'll explain what this what this does later. But okay, so it's taken from A to B, which is A is a complex, or like a compound, B is called a protein channel, and then C is also a complex. And then C, after a while, it's kind of like it doesn't really have that much energy anymore. So then when it reaches photosystem 1, it's kind of at a lower energy, right? And then more sunlight comes through and it recharges the it recharges the electron and makes it again a high energy electron, where then this electron can be passed again to complex D. And then in D is where it meets. It's NADPH is it's outside. It's in the stroma. It's found in the stroma. NADP plus. And so these like high energy electrons is then carried to photosystem D, where it's NADP plus, which is the final electron carrier in the stroma. So then NADP plus picks up hydrogen ions. And then it also picks up because all electrons travel in 2. So this is 2, this is 2. It goes all the way in 2. So it's like this is 2, this is 2. But I don't think you have to write that for the thing, right? So then the NADP plus picks up some hydrogen ions or protons, and then it also picks up the 2 electrons, and it converts into, this whole thing converts into NADPH. This is one of the products of light-dependent reactions, okay? And then another product, and this whole chain that I just explained, it's called the electron transport chain, okay, or ETC for short. So we can write as electron transport chain. Okay. And then another way, because we have multiple products, some of the products, let's just wait for a second. Let's talk about some of the reactants that go in light dependent reactions, okay? Because I think she's going to ask a question like this. Some of the reactants that go inside light dependent reactions could be sun or light. It could be water, which I'll explain. ADP, because the ADP is turned into ATP. I'll explain that too. And NADP plus. Okay, so those are some of the reactants and some of the products that come out of light-dependent reactions could be NADP plus. And then let me explain something. So basically, as this electron is being passed through the whole chain, it is releasing energy, because when these two electrons go to A, it has slightly less energy because it's spending energy. It's releasing energy. So where does this energy go? This energy, it basically, how do I word this? Oh shoot. It provides energy for the active transport of hydrogen ions from the stroma to the lumen. Why does the hydrogen ions need energy to go through the thylakoid membrane? Well, because one, they need to go through, because it's going from a low concentration of energy to a high concentration of energy, because there's high concentration of hydrogen ions in the lumen and low in the stroma. And the reason why is because hydrogen ions are small polar molecules, so they need to go through the protein channel. This is a protein channel right here. So they're going to go through the protein channel and then go to the lumen, okay? And so then, okay, so this whole transport is a one-way transport. So how does photosystem 2 get its electrons? Well, we have some like water, H2O, right? That comes through the roots of the plants, okay? So the plants take this H2O and convert it into and break it down into hydrogen ions and oxygen and 2 electrons, okay? So this 2 electrons recharges the photosystem 2. These hydrogen ions, and then oxygen is just like a byproduct. And then these hydrogen ions, because the lumen is receiving hydrogen ions from here and through from the stroma to the lumen, they have a lot of hydrogen ions. So these hydrogen ions will go through a structure called the ATP synthase. And these hydrogen ions are gonna go through it, and once they go through it, because remember the stroma is low hydrogen ion concentration. So when we're going from high to low, it's gonna cause the ATP synthase to spin, okay? It's gonna start spinning like a turbine, basically. And this energy that's released from its spinning, it allows this enzyme, ATP synthase, to bring ADP and one inorganic phosphate group. They're gonna come so close, because remember that was a property of enzymes, that it brings structures so close together that they literally form and equal ATP, which is another one, product of light dependent reactions. Yeah. So the NADPH, one product, and ATP made from light dependent reactions, they are high energy, and chemical energy is stored through these. And then we're going to see these come up through this Calvin cycle or light independent reaction, because this is only one part of photosynthesis. I think that's all. What else? I think I think we're good. Yeah. Let me know if you have any questions.